To our webinar on sample size calculations. I'm Susan Pumala.
And I'm Chad Berger.
And we're with the Collaborative Research Center for American Indian Health in the Methodology Core. And before we begin the webinar, I just have a couple of things that I wanted to go over. This webinar will be recorded for future use, and after today it will be available at the CRCAIH website. Also, just a note, while we're doing the webinar, all of the lines are on mute. And so if you have questions, please type them into the question box, and we'll stop at a couple of places during the presentation and go over the questions that we receive. And the last thing I wanted to say was, as the Methodology Core, we have a lot of services that you can take advantage of. We provide support for research studies, especially in the design phase of those studies, to help come up with study design, provide analysis plans, sample size calculations, and then also to come up with data management plans. We do some analysis and also data management after your study has begun as well. So if you have any specific needs, feel free to contact myself or Chad or other members of the Methodology Core. So today we're going to go over several things. First, we're going to talk about why sample size calculations are important, and then we'll discuss some of the available software packages that you can use for calculating sample size. And we'll also go over one of the most frequent questions about sample size calculations is how to get the information. So we'll go over an example of gathering that information from previous literature. And finally, we'll use a software called G-Power to do some specific practice calculations for sample size. So the first thing we wanted to talk about today was why sample size calculations are important. So the reason that they're important is really the reason that you're doing research. You want to find meaningful differences between groups. Sometimes groups are two groups for a clinical trial, maybe a treatment group and a control group. They could also be different interventions that you're trying in a community setting. But really what you want to show is that you have this idea and that it really makes some sort of difference in the population or the clinical setting in which you're working. Usually what a researcher does is say that they want to show something that's statistically significant at the end of their study. And the way that you show that is by doing sample size calculations. The one thing that you have to be careful of is that the researcher is the one who has to define meaningful differences. It's not the person calculating your sample size who knows what's actually meaningful in the context of your research. So when you're calculating sample size, if your only goal is to find a statistically significant result, then increased sample size is always better. But really there's other considerations that you want to think about when you're designing your study. First, you want to find something that's really clinically meaningful. So if you have a very large number of people in your study, you can probably find statistical significance, but it's not going to be a big enough difference that actually means something practically. Other considerations are that you want to minimize the number of subjects that are at risk in your particular study. This, I think, is more common in clinical trials research when you think about a drug that you're giving to someone that might be toxic but also might help, say, cure their cancer. So when you don't know if this drug is going to be better or not, you want to expose fewer people to the risks of that drug. And finally, most studies are funded by some mechanism, and you want to use those dollars prudently. So you want to minimize the study cost by enrolling just enough people to be able to show a difference between your groups that's meaningful.
There are many software packages available for performing sample size calculations. Here's a list of some free and commercial software packages that can be used. On the free side, we're going to focus on G-Power today, but some other free software that's available is R, STPlan, PS, and many web-based calculators. Commercial software that performs sample size calculations include PASS, SAS, Stata, SPSS, and most other statistical software packages that are on the market.
So for this presentation, we're going to set up a couple of different examples and kind of go through how you would calculate the sample size for each different research question. So the first one that we're going to talk about is diet and blood pressure. So say we have a new dietary intervention that we think will lower blood pressure. And in this case, we're going to assume that dietary intervention is coffee. That's one of my favorite beverages, and I wish that this were actually true. I don't know if somebody studied it. But what we're going to look at, we're going to set up a control group that's a low-fat, high-complex carbohydrate diet, and we're going to use that as our baseline for the study. And then we're having a test group that will include that diet along with coffee. And the main outcome in our example is systolic blood pressure. So that's kind of the setup of the research problem that we're going to go through, and we'll come back to that and talk about how the different sample size calculations relate to this particular study.
A statistical hypothesis is the research question that we would like to answer. There are two types of hypotheses that we need for a test. The null hypothesis, or H sub O, defines what it means for a parameter of interest to have no effect. In our example, it would be that coffee would have no effect on the systolic blood pressure. The null hypothesis is assumed to be true unless there's evidence against it. The alternative hypothesis, or H sub A, is also known as the test hypothesis. It usually shows a change or effect for the variables of interest. In our example, it would be that coffee changes systolic blood pressure, hopefully lowering it. When conducting statistical hypothesis tests, there's a probability of making errors. The null hypothesis is either true or false. The researcher uses information from a sample to conclude whether there's enough evidence to reject the null hypothesis, or if not, then they fail to reject the null hypothesis. If they reject the null, that is false, then they have made a correct decision. Likewise, failing to reject a null hypothesis that is actually true is also a correct decision. A type 1 error is made when the null hypothesis is rejected and is actually true. A type 2 error occurs when a researcher fails to reject a null hypothesis that was actually false. Let's look at an illustration of what these errors would look like for our example. We can see that our null hypothesis for the problem is that coffee has no effect on systolic blood pressure. The researcher would conclude that there is enough evidence to show that coffee changes systolic blood pressure, or that there is not enough evidence to show that coffee changes systolic blood pressure. A type 1 error occurs when a researcher detects an effect that is not present. This is sometimes referred to as a false positive. The probability of a type 1 error occurring is called the significance level for a test, or alpha. For our problem, we could think of this as asking, how likely is it that we will find an effect of coffee on systolic blood pressure purely by chance? The acceptable cutoff level for the significance level is typically chosen to be 5% or 0.05. A type 2 error occurs if a researcher concludes that there is not an association when there actually is. This is sometimes thought of as a false negative. The probability of committing a type 2 error is called beta. In our example, this probability is like asking, how likely is it that we will find no effect of coffee on the systolic blood pressure purely by chance? The value related to beta is power, which is 1 minus beta. The power of a test is the probability of finding an association that actually exists. The power of a test is typically desired to be at least 80%. The power of a test is directly related to sample size. As seen on this graph, as sample size increases, power also increases. We would like to utilize this relationship in order to find the optimal sample size for our study. So let's look at how each of the following are related to an increase in sample size. Significance level is inversely proportional to sample size. An increase in sample size will lead to a lower probability of making a type 1 error. Power is directly proportional to sample size. An increase in sample size will lower the probability of making a type 2 error and increase the power of a test. A larger sample size allows us to see smaller differences. Data also varies from person to person. A variable like systolic blood pressure probably has a rather large variability. If there is a lot of variability, then a lower sample size is required to achieve the specified power. Higher sample size. In order to perform sample size calculation, we need to gather some required information. The first piece that we will need is the number of tails for the test. If we are trying to show a difference between two values or an effect, we will use a two-tailed test. The next required item is significance level. 0.05 is the generally accepted level for alpha. The third item is power. Setting a level of power of at least 80% is the standard practice. The graph on the bottom of the slide illustrates the relationship between the hypothesized differences, the level for alpha for a two-tailed test, and the value of beta.
So now we're going to go back to our example a little bit and talk about how we select a test and how we get data for that test. So again, we're looking at diet, specifically coffee on blood pressure. The one thing to note is that blood pressure in this example is a continuous variable. So we're going to look at means between two groups in differences in blood pressure. So when you have a continuous variable, usually you want to look at means. And in this example, we're not only looking at means, but we're looking at change over time. So we're looking at the mean change over time between two groups. Since we're comparing two groups, we also need to determine whether our groups are independent or dependent. In this case, this study is independent groups, so there's separate people on each diet. The individuals in the group aren't expected to be related to each other in any way. It would be a dependent study if you had something like if you were testing the two different diets in the same people. So one diet in one period of time and the other diet in the other period of time. Then they would be dependent because they're the same people. We also need to know what sort of differences we might be expected to see in the two groups with regard to systolic blood pressure. And then we also need to know about how systolic blood pressure may vary in our population. When we calculate sample size, there's a number of different ways that you can talk about the differences in change over time. And one of the most common ones that we'll see in our G-Power software is the effect size, and that's called D. So effect size includes both the difference between groups and their variability. So what we'll need to calculate sample size is the estimated mean and standard deviation for our control group and the estimated mean and standard deviation for our treatment group. The last thing that we need to know is how many people to allocate to each group. Usually this is we have equal numbers in each groups, but there's sometimes when it makes more sense to have, say, twice as many or 3 times as many in one group relative to the other. So we're going to get these values, the means and standard deviations, based on previous literature and also the best guess of the researcher. This is, I think, probably the hardest part of sample size calculations is figuring out what those are, especially with regard to variability of your measurement. Usually, nobody's done the study that you want to do, so you don't have the exact measurements of both your control and your treatment group. Especially true for pilot studies, when you're really looking at something very new. You probably have limited data available to you. So it's going to be more based on investigators' best guesses than data in the literature. But for our study, there was a study that came out in 2010 that looked at diet and blood pressure using a 12-week intervention period. So if we were looking at our study, we can use this as the baseline measure of what our control group might look like. So you can see in the red box, I've highlighted systolic blood pressure, and the mean change over time was negative 4.3. So systolic blood pressure was reduced by 4.3 points. And then this study provides a 95% confidence interval. And using that, we can get a measure of variability for blood pressure. So now that we have the data from the literature, we can start to set up and pull in the numbers that we need to calculate sample size. So our mean for a control group is negative 4.3 with a 95% confidence interval from negative 6.5 to negative 2.2. And from that, there's an equation that you can use to get the standard deviation, which we found to be 11.22. And then what you would do now is talk to the researcher, or if the researcher is yourself, then you would try to figure out what's your best guess for the change that would be meaningful over time. For this example, we're going to say a 2-point difference in systolic blood pressure would be a clinically meaningful change over time. So now I'm going to switch it up, and I'm going to go to G-Power and kind of walk you through some of the particulars of that and talk about how we would do this sample size calculation in G-Power. Okay, so this is what G-Power looks like when you open it up. So there's this big empty space and then a lot of different fill-in boxes on the bottom. So the first thing you need to figure out is what your test family is. For this example, we're doing a 2-sample comparison of means, and so that falls under the t-tests. The next thing that you need to select is what statistical test you're going to do, and there's a lot of different options that you could choose from. So in this case, we're going to do means, and we're looking at the difference between 2 independent means. So 2 groups, 2 independent means, t-test, and this is the statistical test that we're going to use. The last thing that you can select is the type of power analysis. Today, since we're talking about doing power analyses at the start of the study, we're going to look at a priori computing the required sample size given alpha, power, and your effect size. So down here in this lower section, this is where we're going to put in our data. So we're going to do a 2-tailed test, and then this is where you put in the effect size. One thing that's kind of nice about G-Power is if you hover over the effect size, you can get this little nice convention for what's a small, medium, and large effect size. So if you have no other information, sometimes this is a good fallback. In this case, we do have other information, so we're going to determine that effect size based on our means and standard deviation. So what we have for a control group, so group 1, we're going to enter in our mean, which is negative 4.3. For group 2, we're going to enter in our mean, which is negative 6.3. And then by our calculation using the data from the literature, we found that the standard deviation of group 1 was 11.22. Since we don't really have any good data for the standard deviation in group 2, we're just going to use the same one as group 1. So we'll put that in as 11.22 as well. Once you have all your information in, you can calculate, and then you can also, in one step, calculate and transfer to the main window. So you can see that we have a small size effect. Our effect size is 0.18 approximately. Then we have to set our significance level, or alpha, and that's set at 0.05. And then we set our power, and in this case we're going to set it to 0.8. Finally, we need to set our allocation ratio, and we're going to say we have equal sample size between groups, so we're going to leave that as 1. Once everything is in, you can hit the calculate button, and it will provide your sample size. So we have equal sample sizes for each group. Total in each group is 496, so we need 992 participants total. Up in the top section is now filled in with a graph, so you can see how your distributions are laid out. And something that's probably more helpful is it also provides a savable file that you can see all of the different requirements that you entered into the study. And so you can save that so you know exactly how those sample size calculations were done. So now I'm going to turn it back over to Chad for another example.
I think before we move on to the next example, we'll pause for a moment and have a quick break for questions. So Emily will go ahead and read us some questions that may have come in during the first section of our talk here.
Great, I have a couple questions here, so we'll start off with this one. Please explain how sample size calculation applies to descriptive research without a treatment or intervention.
So that's a really good question. So sometimes you just want to get a single estimate, and you don't necessarily want to compare two populations. So when you do that, you can do it a couple of different ways. One of the most common ways is to say how precise of an estimate you can get. So I like to think about it in terms of a confidence interval. So how wide is our confidence interval for the study? And then we can use that data for future studies. So we would do a sample size estimate on how many people we would need for a particular length or width of a confidence interval. And if you're particularly interested in that, I can walk through those calculations a little bit more with you, so please contact me.
Great, we have another question. What level of power are grant reviewers looking for in a study design? Is 80 are reasonable? I'm not sure if I got that correct.
Okay. Well, that's another great question, and the standard value is 80%. Sometimes studies will use a little bit higher level, say 90%. The way you can think about power is that's the 1 minus your type 2 error probability. So if you have 80%, you have a 20% chance of making a type 2 error, which seems pretty high. So you can go up certainly higher than that. So if you have a power of 90%, then you're down to a 10% chance of making a type 2 error, which is a little bit better. I've also seen some people have lower values for power or higher values for a significance level, like for a pilot study when you really want to just get some preliminary information and you may not be interested in using the data for a publication, but just to get better estimates.
Is it true that it is okay to not have a sample size estimate for a pilot grant study?
You know, that's a good question. This comes up a lot. I've seen it done where people just say, this is a pilot study, this is the number that we can do. It really depends on the question and the reviewers of whether they're going to require that sample size calculation for a pilot study. It's nice to at least say something, to say what you're going to be able to show at the end of your study, even if you can't show a significance level at the 0.05 level. It's nice to say, this is what we'll know at the end of our study. So I always think it's a good idea to do some sort of power calculation, even for pilot studies.
So for pilot studies, individuals should reach out to you specifically and ask that question?
Yes. Chad and I and other members of the methodology core are happy to help calculate sample sizes for any pilot studies.
Okay, great. We have another question. What if you're interested in comparing means for more than 2 groups?
So we can show you where to go.
Yeah, if you have more than 2 groups, then the test family is going to be a little bit different. You're going to actually use an analysis of variance. And so the test family that you're going to choose is the F test, and then you're going to see the ANCOVA and ANCOVA statistical tests are all located under this. So if you have questions over which specific test you need to use, that would be another good question to email and ask us.
Great. I have another question. I'm still confused about the difference between statistical significance and clinically meaningful differences. Can you elaborate?
Sure, and I think that's really one of the largest misconceptions that people have about sample size calculation is every time I've done a sample size calculation for someone, the conversation usually starts out with, I want to show something that's statistically significant. But I personally think that that's just the wrong way to think about things. What you really want to do is show something that you think would be meaningful with regard to your study question and your population. And so that's where you really want to start thinking about what difference would be important for me to show. And then you can use sample size calculations to tell you how to get statistical significance if you actually see that difference.
Great. I have SPSS and I don't see any options for calculating sample sizes. Where would I find them?
Well, sample size calculations are available in most statistical software packages. They're not always available in the base portion of that software package. So in SPSS, for example, it actually is available, but it's an add-on package that needs to be added on later on.
Okay. And finally, do you always have to use the default values for
Alpha and beta?
Yeah, for alpha and beta.
Again, so we kind of talked about this a little bit before, that sometimes it makes sense to use other values, especially like if you're doing a pilot study, or if you want to decrease your probability of making, say, a type 2 or a type 1 error. You can change those values. We just are going with the most commonly used values in our talk today.
Good. We'll pause at the near the end of our presentation here for more questions. So if you have more questions, please type them into the chat as we go. Next, we'll look at another example using G-Power to calculate sample size. The specific question that we would like to address is whether vitamin D supplementation in infancy reduces the risk of type 1 diabetes. To begin this study, we need to select an appropriate statistical test. Type 1 diabetes, in this case, is considered to be a binary variable, which has two possible outcomes, yes or no. Because of that, we'll compare proportions for the two groups. The two groups are also going to be independent, so we're going to have separate people, either with or without supplementation, and we need to know what sort of differences we might see between the two groups in the type 1 diabetes incidence. In order to test for differences between the two groups, in the incidence rate of type 1 diabetes, we'll need the information about the proportion in each group and the allocation ratio, or relative size per group. These values are usually based on previous literature and the best guess of the researcher. We found from previous studies that about 3% of people without vitamin D supplementation as an infant have developed type 1 diabetes. We think that this percentage can be reduced to about 1% with vitamin D supplementation. We'd like to have an equal number of participants in each sample for our study. So we'll go ahead and go back out to G-Power and see how we can find those calculated values. There's G-Power. Okay. So in this case, as I mentioned earlier, we're dealing with proportions, so we need to choose the correct test family. There is a proportion option under the Z-test, and so we'll choose the Z family, and then under the value, we're going to choose the differences between independent proportions for the statistical test. Once again, we're doing an a priori power analysis, so we'll leave that set as the default. And next, we'll work on entering our input parameters. For tails, we're going to choose 2 to show that there's a difference, and then we'll enter our values for P1 and P2. So in our case, we thought that P1 was around 3%, but we're going to switch it around here, and we're going to do the smaller one first. So we'll do 0.01 for that. That's what we think we can reduce it to. And the P2 is going to be the 3%, or the 0.03. For our alpha value, we'll choose the 0.05. And beta, we'll use the standard 80%, or 0.80 that we have been using. And in our case, we want equal sample sizes, so I'll leave my allocation ratio set equal to 1. Now when I hit calculate, I can see that there are 769 in each of the two samples, giving us a total sample size of 1538. If you would like to utilize G-Power for any of your sample size analysis, the G-Power website is available from the Heinrich Heine University Dusseldorf website at gpower.hhu.de. And there are also some wonderful statistical tutorials available from the UCLA Statistical Consulting Group found at the URL listed here.
All right. So I'm going to go through the summary and a little bit about pilot grant assistance, and then we'll take some more questions. So hopefully today we've shown you that sample size calculation should be based on meaningful differences rather than just looking for statistical significance. And there's a wide array of programs that you can use to calculate your sample size. When you do your sample size, you need to set your error rates and make sure that you have the best guesses for what you think you might see in your study. But if your study is a very complex design, you may need to contact a professional to help out with those sample size calculations. And then finally, I wanted to say, for anyone who's interested in putting in a pilot grant or who's working on a pilot grant, we're happy to help with sample size calculations, and we can help in a couple of different ways. We can help you do it yourself with something like G-Power, or if you have something that's more complex, or if you don't care to do it yourself, we can sure help you just go ahead and do the calculations and send you the information for those. Also, as you're writing those pilot grants, if you need any help with study designs or study analysis plans, please contact us, and we're happy to help you out with that as well. And here's our contact information, and we'll take some more questions.
Great, so I have a couple questions that we've received. I have already collected data for my study and didn't do a sample size calculation. Is it helpful to do a power calculation after collecting data?
Well, it is possible. It's generally not recommended to perform a power calculation after collecting data. It's not going to give you a whole lot of meaningful results as far as what happened in your study. So it's, like I said, it's generally not recommended to do.
Another question we received was, I am getting different numbers using different web-based calculators when calculating sample size needed to compare two proportions. Why would this be the case?
So that's a great question, and one thing that's kind of interesting and a little bit different about calculating sample size for proportions is it's based on certain assumptions, and so depending on what those assumptions are, you can get slightly different numbers for your sample size calculations. The sample size calculation for proportions that we showed today was based on approximation. There's also an ability to do that based on an exact test. The exact test is usually a little bit more conservative and will lead to larger sample size. So most people use the approximation, but like I said, there's different assumptions you can make for that approximation. So it is helpful to know what assumptions your software is making. So if you do come up with different sample size calculations, you can reconcile them based on the assumptions that you're making.
Another question is your methodology core only available to help with CRCA pilot grants?
So our core is available to help with a large number of different things. Pretty much any study that you have in American Indian Health, we're happy to help out with that. So just feel free to contact me or Chad or any other member of our methodology core, and we'd love to talk to you about your project.
And does that also include the research questions? Are you able to help with that as well?
Oh, sure. If you need help defining your research question and how to do it, we can certainly help out with that as well.
I don't see any other questions at this time.
All right. Well, thank you so much for... Oh, wait, another question.
Sorry, we received one more question, right as we stated that. Okay, the sample size required to detect an effect of 0.25 is larger than the sample size. Is size required to detect an effect size of 0.50 with 80% power and a 5% level of significance?
So with all things held equal, as your effect size increases, your sample size also increases. So hopefully that helps answer the question.
Okay, but they can email you for follow-up.
Yes, yeah, feel free to email. If you have a specific sample size question or you come up with a specific anomaly that you're not sure about, contact us and we can help figure out what's going on.
Great.
All right.
Thank you everybody for attending our webinar and for asking questions. Like Susan and Chad said, if you have further questions, please reach out to them directly or at info@crca.org, and those questions will be forwarded on to them.